Welcome back to linear algebra. In this video, we're going to be looking at representations of vectors. Last time, we were looking at we were looking at sets which are linearly dependent or independent. And we saw that linear independence gave us a lot more restrictions on what we could do with linear combinations. Linear dependence gave us some kind of boring results where there were too many different ways to do things. Prior to that, we had been talking about the idea of the span of a set of vectors and the spanning set of a vector space. Bringing those two ideas together today is going to give us tools for representing vectors in an arbitrary vector space in a consistent manner. Let me get my head out of the way and let's dive into this definition. Let's let V be any vector space, and let's pick a set B as a subset of that vector space. We say that B is a basis for the vector space V if and only if both B is linearly independent and the span of B is V. If we have both of those things, then we have a basis. If we are missing one or both of those things, then we are not having a basis. And when we don't have a basis, we kind of have nothing. Before we get into what a basis is useful for, let's take a look at a couple of specific sets. Any vector space can have any number of bases. B-A-S-E-S is the plural of basis. But the standard basis for Rn is one that we've worked with already. It helps if I make these vectors tall enough. The standard basis for Rn is the set of the unit vectors, 1, 0, down to 0, 0, 1, down to 0, and then zeros all the way down to 1 at the end. So in order to show that this is a basis, I think I can say without reservation that B is a subset of Rn. It's a set of vectors in Rn. We showed that this set for R3 was linearly independent. To show that it's linearly independent for Rn is the same basic idea. we want to take a linear combination, C1 times the 1 zeros, C2 times 0, 1 zeros, and all the way down to Cn times lots of zeros, 1, and set that equal to the 0 vector. Using properties of Euclidean vectors, we know that this is going to simplify and become the vector C1, C2 down to Cn. And the only way that that can be equal to the 0 vector is if C. Sorry about that, my computer hiccuped a little. I'm not entirely sure where it cut off, but we have the linear combination equals the 0 vector using properties of the Euclidean vectors. We know that that means that the vector C1, C2 down through Cn is equal to the 0 vector. And we know that the only way that can happen is if C1 is equal to 0 and C2 is equal to 0 and all of the C's are equal to 0. So we can conclude that this set B is linearly independent. To show that it is a basis, we also have to show that its span is equal to Rn. We show that two sets are equal using subset inclusion. First direction is fairly easy. Since B is a subset of Rn, any linear combination of elements of Rn is also in Rn, so the span of B must be in Rn. So what we need to show is that Rn is a subset of the span of B. Let vector little v be in Rn. And we know the definition of Rn. We can write little v as A1, A2 down through An. We can expand that vector. Until we get this, which is exactly a linear combination of the elements of B. And since V is a linear combination of the elements of B, that means that V is in the span of B. And since we don't know anything about vector V except it's in Rn, and we conclude that it's in the span of B, that means that Rn is a subset of the span of B. And since it's also the case that the span of B is a subset of Rn, Rn must be equal to the span of B. So we have B is a set of elements from Rn. We have that B is linearly independent, and we have that B's span is the entire vector space. And that's what it takes to form a basis for Rn. We call this the standard basis for Rn. If there is no context telling you that you should be using a different basis, it's safe to assume that this is the basis that you are talking about in any circumstance where you're dealing with vectors in Rn. But it's not the only possibility. Instead of looking at Rn, because it's kind of annoying to look at things in general, let's take a look at R3. Just picking n equals 3, that previous result gives us that the standard basis for R3, 1, 0, 0, 0, 1, 0, 0, 0, 1. I claim that this set, 1, 0, 0, 1, 1, 0, and 1, 1, 1, is also a basis for R3. To show that something is a basis, once again, we are looking at, first of all, this is a set of vectors in R3. That's an important thing to notice, but generally not a difficult thing to prove. We showed that this was linearly independent in our last discussion on linear independence. So all that's left is to show that the span of this thing is R3. Once again, because we're talking about vectors in R3, the span of those vectors must be a subset of R3. That's closure of a vector space. Properties of vector space, whenever you have a set of vectors in a particular vector space, the span of those vectors, it also must fall within that vector space. So what we have to do is show that we can write any vector we want to show that this vector can be written as C1 times the first vector plus C2 times the second vector plus C3 times the third vector. I don't remember if I've used WTS as an abbreviation in these videos already, but that stands for want to show. Nice way while you're working through something to remind yourself of what your end goal is. If I can show that vector v can be written using this linear combination, then I will have everything that I need. And in fact, I can set this up as a linear equation pretty nicely. A1, A2, A3 is equal to C1 plus C2 plus C3, C2 plus C3, C3 by itself. Turning that into a system of equations. Once again, we could use all of the tools we have for solving systems if we needed to, but this is an incredibly simple system. A3 is equal to C3. Substitute that in up here. A2 is equal to C2 plus A3, which means that C2 is A2 minus A3. Substitute that in. Up here, we get that A1 is C1 plus A2 minus A3 plus A3. The minus A3 and plus A3 cancel each other out. And I get that I can write V as A1 minus A2 times the first vector 1, 0, 0 plus A2 minus A3 times the second vector 1, 1, 0 plus A3 times the third vector 1, 1, 1. Right, and if you work through the operations on Euclidean vectors, you will get that that works out. Everything is fine. Everyone is happy. And we have our conclusion. C is a subset of R3, C is linearly independent, and the span of C is equal to R3. Those are the things we need to show in order to establish that C is a basis for R3. Any vector space has any number of different bases. So don't get too reliant on the standard basis for a given vector space, but it is worth knowing the standard basis for a couple of vector spaces, just so that there's an easy tool to use as reference. And just one more example here. The set or the vector space of polynomials of degree n, Pn. The standard basis there is the set 1x, x squared, up through to x to the n power. I'm not going to go through and prove that this one actually satisfies the properties of being a basis. It might be something interesting for you to look through. I believe that our textbook does go through that in a little bit more detail, but for the sake of time, I'm not going to today. Instead, I want to look at why we care about a basis. Let V be a vector space, and let B, set of U1, U2 through to UN, be a basis for V. Take any vector V in big V. There is a unique linear combination so that V is equal to that linear combination of the vectors from B. Clearly, there must be at least one, because V is equal to the span of B. That's part of what it takes to be a basis. The span of the basis is equal to the vector space. Since V is in the vector space, it must be in the span of the basis, so there must be at least one linear combination. The key idea of this theorem is piggybacking on the idea of linear independence. It turns out that this linear combination is unique. And I'm going to call this a proof by contradiction. Technically speaking, it's not, but thinking of it as contradiction, I think, makes it a little bit easier. Right. Assume that we have not just one linear combination, but two linear combinations. If we have two linear combinations that both give us vector V, we can subtract first row minus second row here, get V minus V, then we'll have C1 minus D1 times U1. We'll have C2 minus D2 times U2. And we'll have Cn minus Dn times Un all the way at the end. Any vector minus itself, by properties of a vector space, must be the zero vector. And so we have a linear combination of the vectors in our basis, which is equal to the zero vector. But a basis is linearly independent. That means that the only way to get a linear combination equal to the zero vector is if each of those coefficients must be zero. And solving that equation, we get that if we set up two separate linear combinations that both give us the same vector, it turns out that we did not set up two unique linear combinations. We set up the exact same linear combination and gave it two different names. It's a common way to prove uniqueness. Assume that you have two different things that satisfy whatever property you're looking at, and then work through until you can prove that, oh, it's the same thing, you just gave it two different names to be confusing. And this property is important because it gives us that notational aspect. The coordinates of vector v relative to basis b. If we can write vector v as c1u1 plus c2u2 down through to cnun, then we can denote v relative to b as the ordered n tuple c1, c2 through to cn. And this will give us a way of working with a vector relative to any basis. Some bases are easier than others. The standard basis for a vector is always the easiest one to find the relative coordinates for. But if you are working with a particular linear transformation and you know how that linear transformation works on an less intuitive basis, you can still use this to write the vector in terms of that basis and use the properties of linear transformations to go from there. All right, two quick examples. If I want to write the vector 3, 5, 2 relative to the basis 1, 0, 0, 1, 1, 0, 1, 1, 1, we kind of did this already in the abstract, but we set the vector equal to the linear combination. We use the properties of Euclidean vectors to condense that linear combination. We get that C3 is 2. We get that C2 is 5 minus 2, which is 3. And we get that C1 is 3 minus 5, which is negative 2. So the representation of 3, 5, 2 relative to this basis B is the ordered triple negative 2, 3, positive 2. Likewise, going the other way, if I have a vector and I know that relative to this basis, we can represent that vector as 4, -7, 5, I can get that that vector is 4 times the first vector in the basis, 1, 0, 0, minus 7 times the second vector in the basis, 1, 1, 0, plus 5 times the third vector in the basis, 1, 1, 1. So working through that arithmetic, I get that our vector is 2, 2, 5. And it just gives us another tool for talking about vectors. Next time, we're going to be looking at this idea of a basis. And it turns out that there are a couple of very interesting things we can conclude about a vector space just by analyzing some properties of the basis. Take a look at some of the practice problems dealing with identifying bases and representing vectors relative to a basis. And I'll see you in the next video.